Now we're going to do more formally trig substitutions. We've definitely covered this in the past, but just in case you want to look up this section, I'll include it. You use trig substitution whenever you have a squared plus or minus x squared in an integral, or x squared minus a squared. To any power. I don't care what the power is. Now, I say you use that. You usually do. For example, if and a is some real number. If somebody asked you to do this, of course a would be 2. Somebody asked you to integrate this, you wouldn't use trig substitution. You would integrate x squared minus, and you would integrate 4x plus c. So you don't always use trig substitution when you have this, but most times you do. Whenever you have a polynomial and x squared minus a squared, or this, or either one of those two, there are two, one with the plus and one with the minus. If you just had that, well then it's a simple polynomial and you integrate it. But now, what if you say have it in the denominator? What if you have 9 plus x squared in the denominator? Now you can remember these rules. I think this is an octan. You can remember them. It's going to be the octan, or 1 over 3 octan of x over 9. You could remember this, or you can use trig substitution. So now, since everything is understood to be positive, that whole thing goes on the denominator. Excuse me, on the hypotenuse. What's being squared there goes here. What's being squared here goes over here. And then you get that the tangent of u is opposite over adjacent. It's x over 3. Why did I pick tangent? For 2 reasons. I didn't want one of their sides to include that. I didn't want to pick a trig function that included the hard-looking part. And by the way, that should have a square root sign. Sorry. So these are the two easier-looking sides. And I wanted to have x in the numerator, so I used the tangent function. I wanted to have x in the numerator. Like I said, there's a little problem here. What was on the hypotenuse should have been the square root of x squared plus 9. Whether this has a square root or not, and it didn't, we put square root. Okay, so this, bringing this 3 up here, this says that 3 tangent u equals dx equals x. Just x. So, taking the differential of both sides, I can get dx. That is why I solve for x, by bringing the 3 up. The right side is just dx, and that is just what I have. The left side will be 3 secant u tangent u. As though that's not true. The derivative of tangent u is secant squared u. So what we're going to get is 3 secant squared u du. So the numerator is 3 secant squared u du. Now the denominator, 9 plus x squared. There's 2 ways to get that. You can square x, that is, you can square this and add 9 to it, or you can look at the triangle and say, you know what, the secant of u is the hypotenuse divided by the adjacent, which is 3, and bring the 3 up here. Now why? Because I want to get closer to getting x squared plus 9. Or 9 plus x squared. Now if I square both sides, This is what I get when I square the left side. When I square the right side, I get x squared plus 9. 9 plus x squared. So the bottom is just 9 secant squared u. Well, the secant squared u cancels out. This 3 over 9 I'll bring out in front as a third. So what we have is 1/3 the integral of u. Excuse me, du. The integral of du. But the integral of du is u. So I get 1/3 of u. Okay, let me erase a little bit. And now we need to figure out how to write u in terms of x. That is, we need to substitute back. In fact, I didn't get 1/3 u, or I did. I should have said I got 1/3 u plus c. Now, using this right here, we could interchange these two. Tangent of x over 3 equals u, so long as I say inverse. So you get 1/3, u is tan inverse of x over 3 plus c. And I'm pretty sure that's what I said we would get a while ago. Thing is I teach you this. I teach you in a way where you can remember it for life or do it for life, because you're not going to remember every trig integral. How about the square root of 25 minus x squared divided by x dx? Well, this is a trig substitution. When it comes to 25 minus x squared, what's positive, the square root goes on the top. So I look for the a squared minus x squared plus a squared. So I see it's 5 squared minus x squared. The term that's understood to be positive, that goes on the hypotenuse. The one that's negative goes on one side, and the 5 squared minus the x squared, the square root of that goes on another side. And I call the angle, say, u. Now I know that the sine of u, again, I want to use these two sides. I don't want to use the one that has the square root. The sine of u is just x over 5. I want to get the x on the top. It's x over 5. So multiplying both sides by 5, I get that. It is just bring the 5 up. Why did I multiply both sides by 5? Because when I take the differential of the right-hand side now, I just get dx, which is what I wanted. When I take the differential of the other side, I get whatever I get. 5 cosine u du. Okay. Now, I know how to write x. That's 5 sine of u. That's just what it says. I know how to write dx. It's in the top. It's 5 cosine u du. The 5's do cancel. And now I have to figure out how to write the square root of 25 minus x squared. Well, if you consider the cosine of u, it's the adjacent, which is the square root of 25 minus x squared, divided by 5. But I can put the 5 up there. Okay, that's exactly what I put on the top. 5 cosine of u. Okay. So the 5 I'll bring in front, and we have cosine squared u on top, and du, and sine u on the bottom. Okay. cosine squared u on the top, du, and we have sine u on the bottom. What I would do is I would write cosine squared u as 1 minus sine squared u times du. And then I divide that by sine u. In fact, I will do the division. 1 divided by sine u is cosecant u minus sine squared divided by sine u is sine u du. Now, the integral of cosecant u, I'm pretty sure it was negative ln of cosecant u plus cotangent u minus the integral of sine u is negative cosine u. And the whole thing gets multiplied by 5. I ran out of room, but plus c. So it's 5 ln of, now what is the cosecant of u? Well, the sine of u is x over 5. The cosecant of that is just the reciprocal. It's 5 over x. The cotangent of u is adjacent over the opposite. Now, the opposite, the opposite also has x in the box, x. That is, that these two, they both have the same denominator. So I'll write it down that way. 25 minus x squared, the whole sum is over x. Plus the cosine of u. The cosine of u is, plus the cosine of u is the square root of 25 minus x squared. Now, since it's being over 5, since there's the 5 in front, they're going to cancel out. So in fact, the 5 only gets multiplied by that ln part. So the answer is 5 ln of that absolute value stuff plus the square root of 25 minus x squared plus an arbitrary constant. Every piece has to be written, every piece of the integral has to be converted from x to u's. Every piece. Not some, not most, all. That's why it's very important that you write dx. A lot of times people, oh, I'm not going to write dx. Why am I going to keep writing dx? The answer is because you want to get the right answer. X squared dx, all divided by, say, the square root of x squared minus 1. Let's not do that one. 4x squared plus 9 in the bottom. How about 4 plus x squared? Suppose we have this with no x squared on the top. So, this is a classic trig substitution problem. Since everything under the square root sign is positive, or since it's a squared plus b squared plus a squared plus b squared or plus x squared, the whole thing goes in the hypotenuse. 4 plus x squared square root. X goes here, 2, not 4, 2 goes there. And the angle is u. 2 squared, which is 4, plus x squared. Well, of course that equals the square root of 4 plus x squared squared. Okay, we know that the tangent of u is x over 2. So 2 secant squared u du is equal to dx. And that's what I want. I want dx. So that's done. That's 2, which I'll put in front. Secant squared u du. Now I need to decide how to write that part using u's. Again, you can square the left side. You can square both of these sides and add 2. You can square both of them and add, I meant to say 4. If I squared both sides, I would get 4 tangent squared u is equal to x squared, and if I added 4, I would get this, and inside here I could factor out a 4, so I get 4 times tangent squared u plus 1, the square root, and the square root of 4 is 2, so I get this 2 times the square root of secant squared u plus 1, but tangent squared u plus 1 is secant u, and secant squared u, and the cosine, the square root of secant squared u is secant u. So I get x squared plus 4 underneath the square root sign is 2 secant u. Or I go this divided by 2. Well, that's secant. Secant of u is the square root of 4 plus x squared over 2. 2 secant u. Okay, what I did over here was a bit harder. But if you don't know your trig identities, that is, if you don't know that secant is the hypotenuse over 2, well, you don't have much of a choice. But nonetheless, the bottom square root of 4 plus x squared is 2 secant u. And the 2's will actually cancel. Okay, and 1 secant in the bottom kills off 1 in the top. So you have the integral of secant u du. And the integral of secant u du, if I'm not mistaken, is ln of secant u plus tangent u. And we can make sure that's right real quickly, plus c. If I take the derivative of this, I should get back secant u. The derivative of ln of anything is you put the anything in the bottom, and the derivative of the anything on the top. The derivative of secant u is secant u times tangent u, plus the derivative of tangent u is secant squared u. Well, from here and here, I can pull out a secant u, and I get tangent u plus 1 secant u remains, and this gets divided by this, secant u plus tangent u, but that's the same as what's in that bracket, and I did get secant u. So there's no doubt in my mind that is the right answer. If you do have a doubt, take the derivative. Make sure. Okay, last thing is we need to substitute back what? We need to convert back to our x's. The secant of u, well, that happens to be right in front of me. Divide by 2, we get the square root of 4 plus x squared over 2. And the tangent of u is also x over 2. That everything's over 2. This was over 2, and this was over 2. I can put the whole sum over 2. Now, let me erase some. Now, if you looked up this answer in the back of the book, it wouldn't say that. If you had this problem in your textbook and you looked it up, it wouldn't say this. Well, it used some property of natural laws. ln of a fraction, even in absolute values, well, that's the same as ln of absolute value of a over absolute value of b. ln of a fraction is ln of the top minus ln of the bottom. That is, this is equal to ln of the top, square root of 4 plus x squared plus x, minus ln of the bottom plus c. But ln of 2 is a real number. It's a constant. It's a constant. Type it in your calculator. You'll get an exact number. Well, you'll get an approximation to the exact number for ln of 2. And when you add c, well, you get a constant. When you add two constants, you get a constant. Of course, if I knew what that number was exactly, well, then I would combine those two constants. And maybe I would get the real number 7, or minus ln of 2 plus 9. If I happen to know that c was 9, I would say it's 9 minus ln of 2. But I don't know what c is. It's any number. If I have a known constant and I add any number, well, I'm adding a different number. It's a constant. Think about it. This is big C. All I know is that big C is equal to little c minus ln of 2. If little c can be anything, well then big C is anything. And that's the answer you would see in the back of your book, or if your teacher did it in class or something. What I'm getting at is, if you integrated some function, and maybe you got x squared plus 3x plus 4 plus c, you would just call this x squared plus 3x plus a different c. That is 4 plus c is just a constant. It's 4 more than any number. Well, you're going to get any number then. Here's a nice one. E to the x integral the square root of 1 minus e to the 2x dx. First thing maybe I would do is I would get rid of e to the x. It's too complicated looking. Let u equal e to the x. Well, then du will be e to the x dx. This times that. That's du. You are multiplying these three things. This times the square root times that. The order you put it in doesn't matter. And then under here I have 1 minus. Just remember that e to the x squared is e to the 2x. But this is u squared. E to the x is u. If e to the x is being squared, then you get u squared. So it's a classic trig substitution is 1 minus u squared. Okay. The way you would do that is the 1 is being squared. It's understood to be plus 1 squared. That goes on the hypotenuse. U is being squared. Since it has a minus, it goes on one of the legs. And the whole square root goes on one of the sides. And since I already used u, I'll call angle V. And now we know that the sine of V is simply u. It's u over 1, which is u. So the cosine of V dV is equal to du. So now I know how to write du. I want to know how to write the 1 minus u squared or the square root of 1 minus u squared. In fact, if I get 1 minus u squared to any power, if I know that 1 minus u squared to the 93rd power is equal to whatever, remember I want to the half power. So I would raise this to the 1 over 2 times 93. And when you multiply those numbers, when you multiply 93 by 1 over 2 times 93, the 93's cancel and you get the power of a half. So I would get what I had to the 1 over 2. So I just want to get 1 minus u squared to any power. In my case, I can get it to be to their half, or the square root. That is, the cosine of v is the square root of 1 minus u squared, adjacent, over the hypotenuse, which is 1. Dividing by 1, the rule is don't do it. Okay. So let's rewrite this integral using v's. 1 minus u squared cosine v. dv, I meant to say du, is cosine v dv. So this is cosine squared v. Well, this is equal to cosine squared v is 1 plus cosine of 2v over 2 dv, dv. The half comes in front. The integral of 1 dv is v. And the integral of cosine plus the integral of cosine 2v is sine 2v over 2 plus e. Okay. Now since we know nothing about the angle 2v, I'm going to use a very known identity that the sine of 2v is 2 sine v cosine v. And there's the 2 over the 2 that's been there for a while. That cancels out. Okay. I'm going to erase the top right. And now we're going to substitute back. There's the answer, but it's in terms of v. Somebody gives you a problem involving x's and you give them back an answer involving v's, they're going to look at you very strangely, like, what's the v? So what is the v? If the sine of v is u, then the sine of u, the sine inverse of u, is v. I interchange the v into u, but then I have to say inverse. And notice I didn't write u, because I want to write what u is. U is e to the x. So v is sine inverse of e to the x plus sine v. Well, sine of v is u, but u is e to the x. So sine of v is e to the x. E to the x times cosine of v. Well, cosine of v is the square root of 1 minus u squared. But if u is e to the x, as we said right here, u squared is e to the 2x. 1 minus e to the 2x square root. K plus c. Plus c. If you want to see it a bit more clearly, it's 1/2 the sine inverse of e to the x plus e to the x times the square root of 1 minus e to the 2x plus c. If you don't believe I'm right, you take the derivative of this and you should get back what's going to be in red. e to the x times the square root of 1 minus e to the 2x. And if you don't, and you didn't make a mistake, well then I did. Okay, let us try one more. Suppose you have the square root of 1 minus x over x. Make that the square root of x. You want to integrate this. Now, you can make two statements. You can say, nothing's being, you don't have a squared minus b squared. Well, let's look at 1 minus x more carefully. Let's see if I can write it like that. Well, what squared gives you 1? The answer is 1. What squared gives you x? The answer is the square root of x. I guess there are two ways of doing this problem. You can recognize it that way right away. Or, what might, and now this is going to give you the same exact result. You might want to say, you know what, this is too complicated. Let u equal the square root of x. Well, then u squared will equal x. So the square root of x will be u, and this will be 1 minus u squared. 1 minus u squared. And notice I didn't say what dx is yet. Now, that's kind of just what I got down here, where I'm calling that u. I got 1 squared, which is 1 minus, if I call that u, I get u squared. Okay, but now I need to write dx in terms of u. Okay, let me erase dx up there. I put it up there so I wouldn't forget that I didn't deal with it yet. Now, I can find dx from here, but I'd rather find it from here. Why? Because the differential of x is dx. I'm done. 1, 2, 3. The differential of the other side is 2u du. So, times 2u du. And the u's cancel out. And I always love to bring constants in front. So I have 1 minus u squared du. The reason it's in this section is not because we're using a trig substitution, but rather we have an integral that involves this, or this, or that. Our integral involves a squared minus x squared. In this alphabet soup, I can say a squared minus u squared. Instead of the variable x, I can say u. I can say b. I can say k. Any variable I choose to use. We have something that has that, where a is 1. Okay, but this integral is straightforward. The integral of 1 is u, and then I should say the integral of 1 du is u, minus the integral of u squared du is u cubed over 3 plus c. So we just have to write down what u is. And don't try to guess. We wrote it down. It's x to the half minus, when I cube x to the half, get x to the 3 halves over 3 plus c. You want to factor out a square root of x? Fine. Square root of x times 1 gives me this, minus x. The square root of x times x. X to the half is the square root of x times x. When you add those powers, you get 3 halves. Exactly what we have, over 3. If you wanted, you can pull out a third. so you wouldn't have a denominator inside. You would get 2 square root of x over 3 times 3 take away x. Okay, there it is. That finishes the section on trigonometric substitutions.